Hello, everybody. Welcome back to VectorLab. Today, we are going to discuss how we can stress test supply chain network at scale on Databricks. And we have with us Ryuta. So, Ryuta, can you introduce yourself?
Yeah, nice to meet you, everyone. My name is Ryuta Yoshimatsu, and I'm a specialist solutions architect at Databricks, and I focus on machine learning and AI use cases.
Amazing. So, let's discuss a little bit the use case. So, what inspired you to cover this topic of stress testing supply chain?
Yeah, so working as a specialist solutions architect, we do talk a lot about supply chain resilience with our customers, especially today. And I can say like almost every customer in retail, consumer goods, manufacturing, and pharmaceuticals, they're looking into building a more data-driven way of building a resilient supply chain network. And this is for obvious reason because of all these import and export tax conversation that's going on. But if you actually look into like the last 5 years, so today's 2025, so we go back 5 years, 2020, and we look at what was happening in the supply chain network. We had COVID-19 hitting and disrupting the supply chain. And 1 year apart from that, what we had was the Suez Canal blockage, which again was disrupting the global supply chain network. In a year apart from that, we had this war in Ukraine starting. All of these events were disrupting the global supply chain market and causing a lot of damages to a lot of companies. So, people argue that this tariff conflict and conversation, it's once in every 100 years event. Maybe it's right. If you look into the specifics of these events, yes, it doesn't happen so often. Nevertheless, if you look into the event that triggers such a massive impact, it does actually happen quite often. And now, because of this, a lot of companies are looking into building a more optimized supply chain network that can withstand such future disruptive events. We're having a lot of conversation around that with customers. And then we came across this, can I share my screen? Actually, and we came across this research paper by a famous MIT professor called David Simchi-Levi, where he proposes a completely data-driven approach to making an optimized decision to build a more resilient, more robust supply chain network. And in this paper, what he proposes is to build a digital twin of your supply chain network and do a lot of stress testing to basically find out which supplier sites are actually vulnerable to these future risks and which are actually not, so that you can reroute your investment and in some cases reduce the cost for mitigating risks. And when we found this paper,
Sorry, just to quickly recap. So what you're saying is that the events might be different, but the stress is quite similar. So even if the events are different in nature, companies get their supply chains stressed a lot, which is why people should care about building such a system. Do I understand that right?
Yes, you're right. And it's also very similar to when financial institutions, they run a lot of stress tests on their investment. In this supply chain network, it's very difficult to calculate the likelihood of such an event happening. When is the next COVID coming? When is the next big epidemic happening? But instead of that, we don't think about the likelihood, but we just assume that these events will take place. And what is the response of our supply chain network under such disrupting? Can it withstand or can it not? If it not, what needs to be changed right now in order to prepare for those future scenarios?
Is this solution GenAI solution or classical ML solution?
It's still a classical solution, but we're also thinking about integrating into a more generative AI agentic solution. But maybe we can talk about that later.
Sounds good.
One thing I wanted to note was that, so we found this amazing paper, and this paper turned out that it's not just a conceptual theoretical paper, but it also is a very practical paper that the professor wrote together with the Ford Motor supply chain team. They actually introduced this methodology into Ford supply chain network, and they observed a massive improvement. And then later on, we found out actually a lot of companies are adopting this methodology. This paper is 10 years old, but it's a really important piece of work, which is adopted widely in industry. So a group of field engineers at Databricks, so it's me, it's Luis Herrera, it's Puneet, and it's Dael. We decided to build this solution natively on Databricks and open source this project so that our customers, also non-customers, can look into the internals and make use of it. So that's the motivation.
Can we start by defining what a digital twin is for a supply chain?
Yeah, absolutely. So digital twin, in a very general sense, is a replica of some physical system that you want to understand more in detail. And the reason why you want to build a digital twin is then because you can do a lot of, you can play around with it to test it, to simulate it, to understand this behavior in nature. And a digital twin of a supply chain network, particularly, is a graphical representation of your supply chain network. And now, if you think about graph consists of two things: nodes and edges. And in this graphical representation, the nodes will be representing your key sites that exist within your supply chain network. So it could be your supplier's production site, it could be your sub-supplier's production site, it could be your warehouses, it could be your production site, it could be your distribution centers, it could be your retailers. And the edges, and these are the links that are connecting the nodes, they represent how the part, the materials, the raw materials, the finished goods, how they're transported from one node to the other. So this is a digital twin of a supply chain network. And you need to build this digital twin using an operational data, such as bill of materials. So which sub-suppliers are delivering raw material to which suppliers, and what is the maximum production capacity of each supplier site? What is the typical inventory buffer level? And all these operational data combined, you build this thing called digital twin. So that's what a digital twin is for a supply chain network.
So it is a data representation or kind of a graph representation of the real world system. We're trying to map the real world into a graph.
Yes, you're right.
Okay.
Yes, you're right. And once you have that mapped out, then the interesting part starts. You're going to start simulating a lot of different disruptive scenarios without caring about the likelihood, and see which disruptive scenario actually causes a lot of damage.
Do you always need to represent it with a graphical representation where, you have those nodes and then the edges are transportation, or are there different? I mean, I don't want to go too much into the details because we want to go into the solution, but I was just wondering, do you always need to use graphs for that?
You don't need to represent it, visualize it as a graphical interface, but nevertheless, it is in nature, it's a graph because all of these sites are connected with each other. And it's always more intuitive to look at the graph and understand why the inventory was routed, not to this downstream site, but to this downstream site. It becomes a lot more intuitive.
How detailed this graph needs to be then? Do you have to map every single liability in your network in there?
Yes.
Yes.
So if you want to be very comprehensive, for example, the research with Ford, Ford had tens of thousands of nodes, and the depth of their layer of the supply chain network was about 10. So they had sub supplier, and they needed to collect the information from those nodes as well in order to run this algorithm. But that's a limitation for a lot of companies today. And in a practical sense, we have companies that's running optimization or stress testing only to a certain depth of suppliers as well. But that's a very important point, that you need to collect this information and build a digital twin out of that.
So since we've defined what a digital twin is, let's define also the difference between time to recover and time to survive.
Yeah, yeah, we're gonna look into this more in detail in a demo later. Mm-hmm. But time to recover and time to survive. So these are two very important notions that are introduced in this stress testing. So there's a very simple way to look at this stress testing methodology is the following. So you build a digital twin, and then you start disrupting these networks, which means that you're going to be removing one node at a time or a set of node at a time from your graph. And every time you remove your node, you re-optimize your network so that under the new configuration, the network is optimized to meet to maximize the business KPI that you're after. For example, you want to maximize the profit, you want to minimize the cost. The network will optimize itself towards that configuration. And now TTR is an important input to this optimization problem. So it stands for time to recover. And what it is it is the duration of time that the site need to recover to its previous state. So imagine you have this one node being disrupted. It's a factory. It catches the fire and it goes out of operation. And it needs 4 weeks for this factory to get back to its normal state and start producing like before and start supplying its material to the downstream nodes. So TTR in this case is 4 weeks. And the core of this exercise is how much financial damage will be accumulated during the TTR. So that's an important input to the optimization problem.
Is TTR something we define, as in I know that if something happens to this factory, it's going to be 4 weeks before it can reoperate?
Yes, you're absolutely right. And this is an input that you need to collect from your suppliers, or you discuss internally within your supply chain team and assign this TTR to a specific disruptive scenario.
And so then, if I understand correctly, you need two things then. One is, what are the KPIs I'm optimizing for? So that if some of the nodes fail, I need to rebuild or reroute my graph in that way so that I'm optimizing for this KPI. And two, is it for each of the nodes I need to have the time to recover?
Yeah, so the first question is about KPI. Yeah, it's there's a flexibility in how you set your KPI. You typically want to optimize a global KPI, meaning that global profit across all your finished goods. So in this graphical representation, these gray nodes are representing your finished goods, the production of your finished goods. And so each one of these finished goods has its profit margin and also demand for the next few weeks. So assuming that this node goes down, you can either try to maximize the revenue or maximize the profit, considering all the finished goods, not just the local one, but all. So for example, if one node is delivering raw material to multiple finished goods, the decision here you need to make is that to which finished goods you want to route this inventory. And for that, what's needed is what is the profit margin of each finished goods, which one is higher, and therefore we deliver it to the finished good with a higher profit margin so that we maximize the global profit.
So do you build a sort of prioritization list depending on which finished good we should prioritize, considering that one node went down and, for example, we don't have enough raw materials? We need to pick which, supplier in the middle of the supply chain is going to get that.
Yeah, that's a spot on question. That's true. Yes. And what guides that priority is which KPI you're trying to maximize. Is it revenue? If you're trying to maximize the revenue, you would route it to the finished good with a higher list price. But if you're trying to maximize the profit, then you would route it to the finished good with a higher profit margin. But that's also an operational data you need to collect to run this exercise. It's a profit margin for the finished goods. That's what we're going to be running for the solution accelerator.
And then the time to recover, is it something you need to define for each node of your graph?
Yes, good question. So it's something that you generally define for each disruptive scenario that you introduce. So a very simple case of disruptive scenario is one node, one sub-supplier side failing. It takes 3 weeks. But there are certain disruptive scenarios where it affects multiple sites. For example, there's a natural catastrophe in a very specific geographical location, and that introduces supplier side failure in multiple locations. And in that case, TTR could be assigned to all these same sites. It takes 3 months, 6 months for all these sites to come back to its normal production site.
Just curious, is there is there any research done on what is the average time to recover for a site? Because I'm not, people know, or if each supplier knows that in case of a disaster, I expect to be back operational in 3 weeks.
Yeah, that's a really good question. So typically, the suppliers would need to give a response when your company is asking for that information. But nevertheless, it could be that supplier gives you more optimistic TTR, which means shorter, than a reality. And for some certain disruptive scenario, maybe it's really difficult to come up with an educated guess for TTR.
Yeah.
So in that case, then we have another metric called TTS. So this stands for time to survive. So forget about TTR for now. What TTS is, this is an output from the simulation. TTS is the maximum duration of time that the network can withstand without losing any demand. So once you disrupt your network, you remove a few nodes from your network, you run an optimization, you decide where to route your inventory, which production sites to ramp up, and so on. And using the inventory buffer, you are still able to meet the demand for some duration of time. And TTS basically gives you that measure. So how long can your network meet the demand without incurring any financial damages? Now, if you solve the optimization problem, and for specific disruptive scenario, TTS is 4 weeks. That means that you can still deliver your demand for 4 weeks. But then if the TTR assigned to that specific scenario is 8 weeks, that means after your 4th week, you're going to start incurring financial damages. So that's when things start bleeding and yeah.
Okay, so then I can use the TTS as like the maximum threshold for TTR.
Yes, exactly. So yeah, the specific scenarios that you need to pay attention is when you have a TTR that is a lot longer than TTS. That means you have a lot longer time where you actually incur negative damage.
And so, like, just to make sure, because time to survive sounds dramatic with the word survive, it's just when it starts losing money, but it doesn't mean that you go completely bankrupt, right? It's just you start losing money either from a revenue point of view or a profit point of view.
Yes, you're right. Whatever KPI that you're looking into, this is when you start incurring negative impact.
And so then are there any strategies to address this gap if you find yourself in that situation?
Yeah, so you can now look into the risk exposure associated with each disruptive scenario from TTS and TTR. The relationship between them, which one is longer, how much longer. So once you've identified a disruptive scenario where the TTR is a lot longer than TTS, what you can do is to negotiate with your sub-supplier, if there's a way to shorten that TTR. Now, again, this is a difficult ask because for some certain scenario, you don't even know how to assign that TTR. The other thing you can do is you can try to elongate the TTS. By, for example, we're going to look into this in the demo, but for example, building up more inventory buffer, that's one way. Or you can diversify your sourcing. This is another way.
Interesting. But then if you buff your inventory, it means you also have costs related to, I don't know, if you have physical goods, you need to stock them. So I imagine it becomes very complicated very quickly.
Yeah, that's right. But so typically, like building up an inventory buffer is associated with a negative connotation, but not for every scenario. But there are certain key supplier sites you just need to guarantee that you have enough buffer to counteract this future disruptive scenario. But what is not good is that you're building up an unnecessary inventory buffer in the sites where it doesn't really matter. For example, TTR is very, very short, or actually a site failing doesn't incur any financial damage because it's well diversified. And to build a inventory buffer for those sites that is a redundant investment. And those are the costs that we can rethink.
And so now I think I kind of visualize what you're trying to solve for this use case is companies with complicated supply chains probably have no clue about all of these nodes they have in the network and what is even the impact if something fails. And now you give them visibility in all of these pieces based on which they can go negotiate, build more product and store it somewhere, and then optimize the whole network. Okay, interesting. And why Databricks then for this?
Yeah, so that's a very good question. So we think there's Databricks really shines in 3 different ways to build such a solution. The first way is that, as we discussed, it requires to integrate a lot of different data from different, from your suppliers, from your sub-suppliers. On Databricks, this can be done using a feature called delta sharing, for example. You can access the data coming from sub-suppliers or suppliers, and you can work together with your data engineers, data scientists on a single lakehouse platform. So integrating data becomes easy because that's the key to building a good solution. You need to have a good data.
Like all of these components of the graph sharing data between them, though.
Also collecting operational data that belongs to each one of those nodes. For example, bill of material data. For example, inventory level. Those production capacity. Those things also has to be updated on a regular basis because inventory level changes over time. So that's one aspect, the data aspect. The second aspect is that a lot of companies have very diversified supply chain network, which spans across the globe. And we're going to look into a small use case and a big use case in a little bit, but in a practical sense, most of the companies have large network consisting of tens of thousands of nodes. And running a stress test, so disrupting node one by one and trying to evaluate the financial damage associated with that, is a pretty compute heavy operation. And you can't do this, let's say in a for loop. It's going to take many days to do that. But on Databricks, we have Spark. We have a distributed framework natively supported. So we can introduce these simulation in a parallelized distributed way so that the optimization exercise that was taking days can be shrunk into a couple of hours with a very minimized cost. So that's the second aspect of it. And the third aspect is a lot of these linear optimization tools or optimization frameworks. A lot of good frameworks are coming out in open source today. Whereas, we do have also really good proprietary tools as well. On Databricks, we support most of them. So it's really up to what you want to prioritize. You want to prioritize the speed, you want to prioritize the accuracy. You can combine different component open source proprietary model and build a solution, customized solution that works best for your scenario. So these are the 3 aspects why Databricks shines in building such a solution.
Amazing. And so should we discuss the architecture of the solution and show the demo?
Yeah, I think it's better if I dive into the demo because, so by the way, this is the paper from the famous MIT professor. And we have this open source project in Databricks Industry Solutions page where, you can clone this repository and, import all the notebooks. So the notebooks is structured just like an architecture. It's going to walk you through one by one what needs to be done to build this solution. So let's look into the first notebook. So this is just an introduction about the project, everything that we talked about right now, why it's important now, what are the tools that we're going to be using. We're going to be using open source framework for distributed compute. We call it, it's called Ray. And we'll be using open source linear optimizer called HICE and a modeling library called Pyomo. These are all open source. And in the first notebook, we go through what kind of data is actually needed to build this digital twin. In this solution accelerator, we're synthesizing this data set with a realistic assumption. But in reality, you need to go out there and collect this data set. And of course, the first question you're going to ask is, what data do we need? So that's what we're going to be looking into. So this is the supply chain network that we had a peek at. It's a small network. And it's called multi-tier supply chain network. It consists of 3 different tiers: the first tier, the second tier, the third tier. The first tier is representing the finished goods. So in this case, we have 5 finished goods. You can think of it as, let's say, a chocolate. You have 5 different chocolate products that you're selling. And for each one of these finished goods, you're sourcing materials from your first supplier. This is your first supplier, direct supplier, you can call it. There are 10 different suppliers. And each one of these suppliers is color-coded, meaning that these 3 suppliers are supplying the same material to each one of these downstream finished goods. And the direct suppliers also have their suppliers, so we call it sub-suppliers. And these are the sub-suppliers. And they're also color-coded based on which raw material they're supplying. And this network can be an arbitrary depth. But we're just like looking into 3-tier network for now. And okay, so what kind of operational data do we actually need to collect? So this is listing the operational data here. So we need to first know, like, what are the nodes belonging to each one of these tiers. So these are the finished good nodes, these are the direct supplier nodes, and these are the sub-supplier nodes. And what are the edges? So this information comes from bill of materials. So which a finished good is consuming which raw material in which material. And we also need to know about the material types. This is the basis for the color coding. And we're also collecting information about the profit margin of the finished goods, as we discussed before, and inventory level, the demand for the finished goods, and also the production capacity, maximum production capacity of each supplier site. So these are all the information that you need to collect in order to build your digital twin.
So then, do you map on the edges how strong is the edge between kind of one supplier and the next level?
Yeah, you can think of it as more like a metadata related to it. Yeah, so it's actually you can see down here below that T11 node is consuming these 4 different raw materials, and and those information as well. So how many raw material units were delivered to the downstream supplier site?
Okay, sounds good. So it's more metadata on the node.
Yes,
okay,
you're right. And this metadata can also include things like geographical locations, product types, supplier types, and so on and so forth.
Nice. Okay, clear. So mainly we need what are our nodes, how they are connected, and how much. And any metadata, other metadata that matters for your business.
You're right. Okay, then let's
go
to the next notebook. So this is the notebook that actually applies stress testing on that small network that we looked at together. And for this, we're going to be using this HIGHS linear optimization framework and also PyOMO, which is a modeling framework. So we're generating the same data set again using the utility function. And we are here constructing this disruptive scenario. In this case, it's a simplistic scenario where we take one node at a time and we remove them from the network. And by node, I mean the node that is in the second tier and the third tier. So the assumption is that, we're going to be running simulations, assuming that each site fail. And for this, we're also assigning a random TT. And so it's a little bit hidden into this custom function.
So you are assigning a random TTR for the node that is going to be disrupted.
Yes, you're right. Yeah, and we're running this utility function build and solve multi-tier TTR, which is defined inside this utility script. So you can dive deeper into the content, but what's happening here is it's using PyOmo to define that optimization problem. And that optimization problem is formulated in this fourth notebook, if you're interested in the mathematical definition. So we're minimizing the lost profit, global lost profit under these constraints. So these constraints are like real world physical constraints. For example, you can't produce more goods than you received the raw materials for. So it's a very sensible.
But like in this case, then we have defined the optimization method to be optimizing the profit margin.
Yes, exactly.
Yes.
So minimizing the loss, profit loss. Yeah. And it's going to get a little bit more clear once we see the result. So PyOmo is a very flexible framework that allows you to convert that mathematical definition, equalities into an actual programming. So we're using that. In this simple scenario, we're actually iterating through each one of these disruptive scenarios. We're not thinking about parallelization yet.
Okay.
So yeah, so I'm listing the outcome. And these are all the disruptive scenarios. So nodes associated with each one of these disruptive scenarios. So in this case, it's T2_1. TTR is for whatever the unit is, 4 weeks. Let's take it 4 weeks. The optimization program was able to find an optimal global minimum, and the profit loss was 0. So when this node goes down for 4 weeks, actually doesn't incur any negative impact. But when this node goes down for 8 weeks, and it's going to start seeing the lost profit, which is 509, let's say $100,000. And then what you can do now is you can rank by the size of the lost profit. And what we're doing is exactly that. So we are ranking the nodes that would incur the biggest loss once they fail for a given TTR. So here, first of all, you can see that all of these nodes have relatively large TTR, 8, 9, 10, 10, 8, and then pretty big loss profit in whatever monetary unit that is. So
question here, because you did a for loop and you said like here you didn't need to leverage like Spark yet. When do you start needing to parallelize that? Is it because here we're just showing the art of the possible and then we'll see when there's a lot to process? Or are you always okay like just doing this for loop?
Yeah, so this is like still a relatively small network, which consists of 1, 2, 3, 4, 5, 10, and maybe like 25 scenarios. And iterating through this 25 scenario is not, it's okay. It finishes in a couple of minutes. But in the next notebook, we're going to start seeing like thousands of nodes. And iterating through them simply is not viable anymore. So that's when we start introducing Ray and doing this disruptive optimization in parallel.
Amazing.
In this case, let's say that T2_10 incurs the biggest loss in profit. So then what does this mean for me? That then, okay, this has a huge TTR. So one is go to them and see, is there any way we can drop the TTR? Or two?
Inventory, is that what you were saying?
More inventory, or in this specific case, the reason why there's a high loss profit associated with this T210 failure is because this is a single source of this specific material. It's color-coded green, and that's why it's a very important node that delivers raw material to 3 different finished goods. So once this node goes down, it incurs a direct loss into this finished goods. And all the inventory that was stocked up here will be routed to the finished goods that has the highest profit, basically.
So then we're saying find another provider?
Yes.
Okay.
Yes. So this is a very intuitive case, E2_10. I mean, like with this size of supply chain network, you can easily guess, okay, this is the most important one. But a little bit more nuanced example is T2_8. It's this guy here in the middle. It is actually diversified. It's got 2 other suppliers supplying the same raw material. And this is supplying material to finished good 5, finished good 3, and finished good 1. If you look into finished good 5, it's actually diversifying its supply to its neighbors.
Yeah.
So this is not a problem. This finished good can be still delivered. But if you look into the third one in the first one, it's actually not diversifying. So this is the single source of its material for T3 and also for T1. So this is why when this node fails, T1.5 is okay, but T1.1 and 1.3 is start failing.
So it's also showing we not only which if one node fails, how the rest of the products are impacted, but also which are the products I need to start diversifying even more, right?
Yes.
Yeah, okay.
You're right.
Cool.
And very similarly, like T3.15, which is the single source material provider for the C28, is also classified as a high impact node. And this is because it is delivering to already a high impact node here, T28, and this is a single source of that material with a long TTR. And that's why the optimization algorithm is able to find that this node is also a risk.
The optimization work behind the scenes. So let's say that T3_15 edge is removed to T2_8. Does it then try to find, given all the other nodes and the existing network, what do I need to change?
Yes. So I'm going to look into the next cell because that's addressing exactly what.
Okay.
The beauty of this optimization algorithm is that you get to access all those detailed information. So I found out T28 is an interesting case when it fails. So I want to run a more detailed analysis. So I'm actually running the same function for this scenario again. And now I get to access something called all the decision variables, meaning that so after the optimization, this is the information that I have access to. So if you look into first, so this is the demand, the production volume, the inventory level, and the lost demand. First of all, because T28 was disrupted, its production capacity is now 0, which makes sense. Now, it had an inventory of 1,569 units. And now, if we look into the finished goods, we can see that it impacted 2 finished goods, 1 and 3, because the lost demand is positive. It means that we lost actually demand. And this is what we saw also in the network, that T11 and T13, they were not diversifying its source. That's why it's incurring these 2 losses. Whereas T15 is not incurring any loss because it was diversifying that specific raw material that T28 was delivering. And now, if you look into T11 and T13, you can see that T13 actually completely stopped the production. But T11 actually kept the production. And this is because it's 1569. This was this stock that was kept in this T28 was directly routed to T11. And the reason for that is because the profit margin is higher for T11 plus the demand that was to expect. So demand times the profit margin was higher for T11. This linear optimization program, it decided to route this inventory, all of them, to T11 instead of T12.
Yes, interesting. Curious to see, I see maybe how GenAI could help here, as in, given the results, interpret them for me. Like, what do they mean? What should they act upon?
Yeah, especially
Yes.
for business stakeholders who are constantly asking for various scenarios. Is there a way to integrate that so that they can get answers to their natural language questions?
Yeah. So this professor David Simchi-Levi, I think yesterday published a paper and also an article in Harvard Business Review that says exactly that. because now the business executives, supply chain managers still need somebody like me, a data scientist, to come and tell you, okay, this was this. But this could potentially be all replaced by an LLM. For example, the formulation of the disruption. You just provide a natural language input. Okay, there was a tsunami in this specific coastline. And then it will be able to select that set of nodes that were disrupted by this input by looking at the metadata assigned to each node. And then it will come up with a set of disrupted nodes and then run an optimization problem. And also, by the way, the agent can have an input as which KPI to maximize, whether the supply chain manager is looking into maximizing profit or minimizing cost or maximizing revenue. And it chooses the right tool, optimization algorithm to perform that. And then once it receives the results back, the result will look like this, and then it can reformulate in a natural language what needs to be done. So in this case, the agent will specifically say route all the inventory from T28 to T11 because the profit margin higher, and we're able to achieve higher profit by doing that. Yeah, so this is really cool. You can also run the simulation in like all sort of scenario. For example, you have a surge in demand for a very particular product. Surge in demand is also a disruptive scenario. For example, your competition is failing to deliver this competitive product, and now the demand is spiking 2 times, 3 times the standard level. And you're going to run an optimization algorithm to see which supplier production sites ramp up to meet this demand. Are we in a good position to do that? And yeah, all of the things can be done by a natural language. And this is something that we're working on right now.
You do. Very nice.
Yeah, it was actually partially inspired by your solution, Lara, with a supply chain optimization agent.
Well, I can't wait for you to come back and present that, because that would be, amazing for the industry if we had that type of solution. And there's so many ways to go about it. Do you give business stakeholders, some filters, give me 10 scenarios for this particular KPI, etc.? I think there's just so many ways to approach this. It's very interesting. But I love it when you have ML problems, traditional ML problems, and then you wrap, that as a function that can be leveraged by an agent. Love it. So cool.
Yeah, so very quickly running through the rest of the notebooks. So TTS is actually a different formulation, mathematical formulation that gives you the output of TTS. And you can also do that. You can also recover TTS and compare that against TTR. And the risky nodes are obviously the one with longer TTR. Yeah, and you can find that out. And in the next notebook, what we're doing is now we're expanding the size of the network. I'm not visualizing it anymore because it's really big and it doesn't fit. But you can think of it as we have 200 finished products, 500 direct suppliers, 1,000 sub-suppliers, and we're running that disruptive scenario one by one. And we're using Ray to do that.
Can you just recap what Ray is in just a few sentences, either you or Maria, maybe just for the people who don't know what Ray is?
Go for it, Ryuta.
Yeah, Ray is a distributed computing framework. It's open source that allows you to run, for example, this simulation in parallel at the same time. So now we consist of 1,700 scenarios, and they're all independent from each other. So they can actually be tackled in parallel separately, right? Array allows you to do that, to take that specific scenario and distribute it to different cores that exist in your cluster. And it's very, so it's very efficient. And now the interesting part is this. By running all the simulations, so this consists of 1,700 data points. We are looking into this one dimension called lost profit. So this is exactly like how much loss will be incurred when a given node is disrupted for a given TTR. You can see that these are the risky nodes. So here we're also plotting it against a total spend for any risk mitigation measures that we're taking for each one of these nodes. So this is also assigned randomly. And now the sites that you want to look into is in the red box. So these are the supplier sites that actually incurs a lot of damage when it fails, but we're not investing that much into their risk mitigation. So this is we need to reconsider and maybe invest more. And the ones in the green boxes are we're investing a lot for risk mitigation, but actually it doesn't really matter when they fail because you don't get any financial impact from that. So for example, you can take the investment that you're making in this green box into red box and build a more resilient supply chain network. So this kind of things you can do if you run a comprehensive set of disruptive scenario.
This investment may look like, for example, not having so many providers for this and good, or not having so much storage for this, or something like that. Yeah.
Yes,
Yeah?
yes, you're absolutely right.
Cool.
Yeah, so that was it. The very quick walk through of the solution, and yeah, and the team is building, adding an agentic layer on top of it, and yeah, please do look forward to what's coming.
Thank you. That was amazing.
Absolutely amazing. This is also, I love that then you have this graph with overinvestment, underinvestment. You could put that in a slide to business stakeholders and it's very clear, visually, like how you could save money, which is what they often care about. So I think it's very, very cool.
Thank you.
Thank you.